So electrolysis is sort of the opposite. We're taking electrical current and we're driving a non-spontaneous reaction. That occurs in an electrolytic cell. So the reaction between hydrogen and oxygen to form water is spontaneous and produces electrical current. That's the basis of the hydrogen-oxygen fuel cell. But by supplying electrical current, we can cause the reverse reaction to occur. So we could use a solar-powered electrolytic cell to generate hydrogen to use to power fuel cells, right? That could be a thing. So here's an external source of electricity. Here it looks like a lead-acid storage battery. And we've got a cathode and an anode in some water, and we are basically destroying the water, breaking it down into hydrogen and oxygen. And you can collect the oxygen gas in one container and the hydrogen gas in another container. Now, obviously, it's not practical to use balloons, but you get the idea. So there are a lot of other uses of electrolysis. How do you get pure metals? Not all metals can just be found in the ground, right? You can find gold because it doesn't react very much, but you don't actually find things like iron just as chunks of iron. You find them as iron in compounds. How would you make pure sodium metal? Sodium metal reacts with water, it reacts with pretty much anything. So it's not stable. You're not going to be able to find it somewhere. You have to make it, right? So you can take sodium chloride and using electrolysis produce sodium metal. Electrolysis is also used to plate metals onto other metals. So silver-plated tea set or whatever, instead of making the whole thing out of silver, which is very expensive, you can make the item out of a less expensive metal and then just put a layer of silver on the outside. It's called silver plating. And that would happen something like this, where you've got silver ions in solution, and you're going to oxidize. We're oxidizing silver over here, and we're reducing it over here. And so you can take the silver from the silver electrode and deposit it on an object. It's not a spontaneous process. The voltage that's needed to produce electrolysis will depend, of course, on the specific half reactions. What you do in electrolysis is the cathode and the anode are reversed. So here we've got a zinc half cell and a copper half cell. And for the voltaic cell, the zinc is the anode and the copper is the cathode. If we make an electrolytic cell, we're using a voltage source here, we're forcing electricity to flow the other way. And that makes the zinc the cathode and the copper the anode. They're opposite because oxidation always occurs at the anode. And so what we're doing is we're switching the name of the electrode rather than what happens there. So here we've got a summary of electrochemical cells. We always have oxidation at the anode, reduction at the cathode. In a voltaic cell, the anode is the source of electrons and the cathode draws the electrons. In an electrolytic cell, electrons are drawn away from the anode, which is connected to the positive terminal of a power source. So the positive terminal is pulling electrons away. Instead of the electrons running away, they're being pulled away. And then the electrons are forced into the cathode, which is connected to the negative terminal. And so the negative terminal of the battery or source of electricity repels the electrons and forces them into the cathode. So how do we know what's going to happen, what products we're going to get when we do electrolysis? So if you're using a pure molten salt, so you can actually melt sodium chloride, can be done. The anion gets oxidized, the cation gets reduced. There's nothing else that can really happen. So here we have molten sodium chloride and 2 inert electrodes. And so we're forcing electrons in here, making the cathode negative. The sodium ions are attracted to that. They're gaining electrons, so that's reduction. Sodium is being reduced to sodium metal. And over here at the anode, the chloride ions are being oxidized to form chlorine gas. See the typo in that equation? Why is there a negative sign on the Cl2 gas? What? If your molten salt has more than one cation, what the product that you get will depend on which of those is more easily reduced. So here's an important note. Those standard cell potentials in standard electropotentials in table 19.1 don't apply to molten salts. Those are for an aqueous solution. The relative ordering is the same though. So if we look at a mixture of sodium chloride and potassium chloride, we can look up the electrode potentials for sodium and potassium. So to reduce sodium is 2.71 volts, and reducing potassium is 2.92 volts. So it's easier to reduce sodium than it is to reduce potassium. So most likely you will get sodium metal instead of potassium metal out of that reaction. If you have more than one anion, same thing happens. Which anion is more easily oxidized? So if you've got sodium bromide and sodium chloride, well, you can look at this. We've got the bromide. These are oxidation reactions, right? E0 minus 1.09, E0 minus 1.36. And this is where, in my mind, things get kind of confusing, because the book's approach is no matter how you show the equation, they're going to show the reduction potential. So the reduction potential is opposite in sign to the oxidation. So the oxidation for this one would be plus 1.09 volts, and for this would be plus 1.36 volts. So which one is easier to oxidize? This is going to be the bromide. So the bromide requires 1.09 volts. The chloride requires 1.36 volts. So I've got there in brackets. I prefer that when we reverse the equation, we change the sign. And then if you're looking at a list that has the positive at the top, the higher reaction is always going to be easier. In the textbook, they always give the reduction potential, even if they show the oxidation. I think that's really, really confusing. Any questions? So that's molten salts. In aqueous solution, you've got the additional complication of possibly electrolyzing the water itself. So we've got our battery here, and some of you who are sitting closer can probably see that there's bubbles coming up. Right now I'm just seeing bubbles from the one electrode. Eventually there will be bubbles from both. Look, it's snowing. So we can oxidize water to form oxygen gas. We can reduce water to form hydrogen gas. So these are their potentials. I'm just looking at this and trying to figure out what is this over here. Okay, so after examining this slide a little bit, I think I remember what it means. So this is a standard potential. Standard potential means gases are present at 1 atmosphere of pressure. Aqueous things are present at 1 molar concentrations. So obviously in pure water, that's not the condition. And so you can calculate the actual potential under the actual conditions. And so for the oxidation, this is minus 0.82 volts, and for the reduction, it's minus 0.41 volts. That's in pure water. So in pure water, add those together, you get a cell potential of negative 1.23 volts. So if you apply 1.23 volts or higher, then you can electrolyze the water. Now, pure water doesn't conduct electricity, so it's kind of hard to do that with, which is why in my little demonstration here, I use tap water, and then just to speed things up a little bit, I've been tossing some citric acid in here just because that's what I have available. Because if you have no ions, oh, now I got black stuff floating in there, that's great. If you don't have any ions to conduct the electricity, then the chemical reaction can't occur. Because what's happening here is I don't have a wire connecting the 2 terminals of that 9-volt battery. This isn't going to work with like a AA or a AAA battery, because what's the voltage on those? 1.5 volts. So it's only just barely above that, and it's just not going to work as well. The 12 volt will work a lot. I mean, the 9 volt works a lot better. So if we look at a sodium iodide solution, so we've got 2 possibilities for the oxidation. We could oxidize the iodide, or we could oxidize the water. When we look over here, the actual potential for the water is minus 0.82. The standard potential for the iodide is minus 0.54. The reduction, we've got the possibility of water being reduced or the sodium being reduced. The water is minus 0.41 volts. The sodium, under standard conditions, is minus 2.71 volts. So at each electrode, the half reaction that is easier, the less negative, will be the one that actually occurs. So up here, we're going to have the iodide being oxidized. But down here at the reduction, the water's going to be reduced, not the sodium. So we cannot produce sodium metal from an aqueous solution because instead of reducing the sodium, we reduce the water, right? So that's why that would need to be done from a molten salt. On a molten salt, because it's a liquid, the ions can move and can conduct electricity so that you can have that reaction occurring. But if you have water in there, you're just going to reduce the water. So here's an illustration of that cell. What do you notice about this cell that's a little different than the electrolytic cell? No salt bridge, right? We don't need a salt bridge because we're not separating two spontaneous half reactions so that we can force the electrons. Here, this isn't going to occur on its own. We're forcing electrons through here, and so we don't need this to be separated. Any questions? So just to make things a little more fun, overvoltage. Some non-spontaneous reactions require more voltage than you would think, than you expect, than is predicted, before they will occur. So this is awesome. Due to kinetic factors beyond the scope of this discussion, the actual voltage required for the oxidation of water is about 1.4 volts, not 0.82 volts. Just because.